So welcome back to the session on the free vibration. So we are continuing the problems. So let us consider a problem. Write a differential equation of a motion for the system shown in the figure and find the natural frequency of damped vibration and damping ratio of the system. So the system consists of a spring, a mass, and a damper. The spring is at a distance of A, damper is at a distance of B, and mass is at a distance of L. So at this point I'm going to consider equilibrium position. So when I want to move the mass downwards or upwards, it will be going for a inclination theta. So because of that, if I push the mass downwards, the spring will be expanding and damper will be also acting. The damper will be pushing the mass upwards and the spring is trying to pull that mass upwards again. If I want to push the mass upwards, the spring tries to push it down and damper try to push it up. So whatever the direction I am going to give for the mass, the opposite direction K and C will be acting. So let us assume the mass is displaced by theta. So spring force will be K into A theta, damping force will be C into B theta dot. The moment of I dot equals to ml square. So as for the Newton's method, what you have seen the free and damped vibration. So it will be equals to I theta double dot will be equals to the forces acting. The force is K A theta. So when I go for that, it's going to produce the anticlock. I'm going to take as minus K A theta into A. Similarly, the damping also. So minus C B theta. B will be the perpendicular distance from the equilibrium position. So when I'm going to simplify that, I'm going to get an equation theta double dot plus CB square by ML square into theta dot plus KA square divided by MC square into theta equals to 0. So this is the equation. So for that, solution will be as 1 comma 2 will be equals to, that is minus B, that is CB square by 2MC square plus or minus root of CB square by 2MC square minus KA square by ML square. So to find CC, so for finding the CC, so the inside term should be equals to 0. That is a critical damping. Then only you can say that is a critical damping. So that I want to consider. By simplifying that, I want to get an equation. CC is equals to 2AL divided by B square into root of Km. So by substituting the values again, I want to get overall CC is equals to 2AL by B square multiplied by root of K into M. That will be the critical coefficient of friction. Sorry, critical coefficient of damping. So let us go for the next problem. That is, write the equation of motion of the damped pendulum as shown in the figure, assuming the rod to be massless. So find the natural frequency and the damping coefficient of the system for which the system is critically damped. So they give clearly given it is a critically damped one. So the mass of the string has been left out, that is neglected. So length will be L, mass is kept over here, and K and dashpot over here. So when I want to pull the mass this side towards the left hand side, the K and dashpot, that is the damping, will be acting on the right hand side. So which tries to pull the mass on the opposite side. So if I give the anti-clockwise as the motion, this two will go for anti-clockwise motion. Since both K and C are in the same distance, so spring force will be K into L theta. K will be the stiffness, L will be the length. From the equilibrium position, theta will be the angle of deflection. The damping force again C, L, again it going to get as theta dot. Theta dot will be the angle and L will be your length or distance between from the equilibrium position to the damping. So I naught will be equals to ml square. So as for the Newton's method, I naught theta double dot will be equals to KL theta, which is going in anti-clockwise direction. I want to take as minus, and perpendicular distance is L. Similarly, CL theta, so again we're going to get as minus. Since there is a mass, so the mg will be acting downwards. So when the mass is on towards the left, again the mass will be, that is gravitation will be acting downwards, which also tries to pull the mass to the equilibrium position. So that also will go for a negative condition. So that is anti-clockwise direction. So that also I want to consider minus mgl into theta. So by substituting all the values, so I want to get the equation like this. So I want to simplify that by dividing all equation by m. So I want to get as theta double dot plus k by m theta plus c by m theta dot plus gl by gl into g by l into theta. So by simplifying that, I want to get as theta double dot plus c by m theta. If I want to take common, km plus g by l multiplied by theta equals to 0. So by finding the solution for this in terms of minus b plus or minus root of b square minus 4ac divided by 2a. So I want to get the overall equation as 1 comma 2 will be equals to minus b, that is c by m multiplied by 2, that is minus c by 2m plus or minus root of c by 2m square minus KL plus GM divided by M into L. So for a critical damping, C by 2M should be equal to this values. So I'm going to substitute that value. So when I want to substitute, I'm going to get the equation that is CC is equals to 2M root of KL plus MG divided by M into L. So CC will be equals to root of 2 root of M KL plus MG divided by L. Or you can simplify that. So damped natural frequency will be equals to root of KL plus MG by ML minus C by 2M whole square. So coming to next problem, a machine has a mass of 200 kg. It is placed on two different isolators. The corresponding amplitudes records as shown in the figure. So determine its characteristics and undamped natural frequency. So this is the frequency has been received from the machine. So you can see that it is gradually reducing, that exponentially reducing to the zero. So it is an underdamped system. So initially it is amplitude of 1.52, the second will be 9.5, 0.95, and there will be 0.6, 0.38 and 0.24. So x0, x1, x2, x3 and x4. So the time period will be 0.38. There will be 1, 2, 3, 4, 4.5 cycles you're going to get. So when you're going to go for the logarithmic decrement, so delta is equals to 1 by n ln x0 by x4. That is from first amplitude, that is x0 to x4 will be 1, 2, 3 and 4 cycles. So I'm going to take n as 4 and this ratio I'm going to substitute. So I'm going to get as delta as 0.461. So delta, once you know the delta, I can find out the damping factor. So delta is equal to 2 pi damping factor divided by root of 1 minus zeta square. So when I want to get this value as very less, so I'm going to assume that delta is equals to 2 pi zeta. So zeta is equal to delta by 2 pi. I'm going to get as zeta as 0.073. That is the damping factor. So once the damping factor is known, so I have to find a damped natural frequency, that is the omega d is equals to 2 pi by Td. So Td will be equals to T by N. So time taken for total period is 0.38 divided by 4. I'm going to get as 0.095 seconds. So omega d will be equals to 66.13 radians per seconds. So the natural frequency, so omega d will be equals to omega n into root of 1 minus zeta square. So from this equation, when I want to substitute omega d and zeta, I want to get natural frequency as 66.30 radians. So when I go for the next, so omega n is equal to root of k by m, that is 66.30, and m value is given as 200. I can get k value as 879.1 kilonewton per meter, and the critical damping Cc will be equals to 2m into omega n, that will be equals to 2 into 200 into 66.30. I am going to get as 26,520 Newton second per meter. So once I got C and Cc value, so I got zeta and Cc value, I can find out the coefficient of damping. So I will be getting as C is equals to zeta into Cc. C will be equals to 1943 Newton second per meter. That will be the damping coefficient. So in further problems, we're going to see in the next video.